Okay, for our second day in Chapter 5, I thought I would stick with doing sample problems. And the two problems today have to deal with friction. How do we add this into our problems? All right, so this is a problem from mastering, or from the back of your book. We have two masses connected by a rope, and then there is a force applied to one of the boxes, and is going to move the boxes at a constant velocity. There is friction between the crates, the boxes, whatever, and the surface. So we are going to have to deal with friction. So the first part of our problem is we want to find F in terms of things that we know, which are the mass of the two boxes and the coefficient of friction. So we're going to look at this as a whole. We're going to be concentrating on the two blocks together instead of looking at them individually for the first part. First of all, let's try to identify different forces acting. I have the normal force on B and its weight. I have the normal force on A and its weight. And then there's also the force of friction between each box and the surface, and I'm going to call these F sub A and F sub B. So those are all the external forces to the two masses connected together. The velocity in this problem is constant when the force is applied. The objects are moving at a constant velocity, and this means that the acceleration is 0. So, first of all, let's look at forces in the y direction equal to 0. And here we're going to cheat a little. We're going to concentrate on each mass alone because we want to show that basically the normal force of each object is equal to its weight. So when I look at mass A, I have the normal force acting upward positive, the weight acting down. So the normal force on A is equal to its weight. We can do the same thing for mass B. And so both of these normal forces are equal to the weight. That happens a lot, but we never should assume. We should also always try to figure it out. So we're going to use the normal forces because the frictional force is always the coefficient of friction times the normal. So the frictional force acting on mass A is the coefficient of friction times the weight of A. And the frictional force of B, similarly, is going to be mu sub K times the weight of B. We're going to use those later on. So now, what we're ready for is to look at the forces in the x direction, because this will allow us to find an expression for F in terms of all the other known quantities. Force acts to the right, and then we have our two frictional forces opposing that force. Those are the only horizontal forces we have, and those are going to add up to be 0. Here we go, just to remind us what we had. We rearrange to find the force of friction, the applied force. And that is our expression. In the second part of the problem, we want to find the tension between the blocks. So when we do this, we're going to look at the blocks separately. So say I have block A, I have the frictional force acting on it, I have its weight, I have the normal force, and I have the tension. So I want to figure out what the tension is. That's going to be force in the x direction, so I'm going to look at that. I have tension minus force, frictional force on A is equal to 0. And so we find it actually pretty easily. But I would also like to show that we could do this with mass B as well. So let's look at mass B. Forces on B are a little bit different because we have that applied force, and then the tension acts in the opposite direction. Look at forces in the x direction once again. Oops, forgot the friction. And I could rearrange this and solve for t. Oops. And I'm going to substitute in my expression for f. If you remember, we found in the previous part of the problem, f was equal to mu sub k times g times the sum of the masses. I'm going to substitute this in here. So T is equal to minus mu sub k mbg plus mu sub k g m sub a plus m sub b And look, this goes away, and once again, we find this is the expression for tension, which of course it should be the same regardless of which mass we focus on. Alright, so now we're ready to look at another problem, and I chose this problem not only because it has friction, but because it also has an inclined plane, and you use some information that you learned in a previous chapter. Alright, so we have this inclined plane. Alright, so we have our incline here. So this is our ramp for our packages. Here's the mass. And it's going to be going sent up the incline with some v, and what we want to know is when it gets to the very top of the ramp, it's going to be decelerating. I want it to get to the very top and come to a stop. The angle of my incline is 37 degrees. My coefficient of friction is 0.3, and the total length of my incline is 8 meters. Alright, so I'm going to find the forces. So my normal force, my weight, and my friction, which is down the incline because the object is moving up the incline. Keep in mind my acceleration is also going to be down the incline because it's going to be negative. So forces in the y direction will allow me to find my normal force. It's normal in the y component of weight. In the x direction, I do have acceleration. I've chosen first up the incline is positive, down the incline is negative. So both my forces are negative because they're down the incline, but so is my acceleration. So I can just multiply by a -1 to make all these positive. Oops, sorry. That's a cosine. I can divide through by the mass, and my acceleration is mu times g times the cosine of 37 plus the sine of 37, which gives me 3.55 meters per second squared. That is the acceleration down the incline. What I'm going to do is I'm going to use that acceleration to find V initial when V final is going to be 0 after a displacement of 8 meters. So one of our kinematic expressions is really handy for this. The one that relates velocity, acceleration, and displacement. This is 0. This is what I'm looking for. My acceleration is minus 3.55. My displacement is 8. This allows me to find my initial velocity, which is 9.9. Sorry, that was the wrong one. 7.54 meters per second. So that's the first part of the problem. In the second part of the problem, we want to, the box is going to get to the top of the ramp, but it's missed by the person and it's going to start sliding back down. So we're trying to find out the speed at the bottom of the ramp. The initial is 0. It starts from rest. Now, you might think it's exactly the same situation, but let's think about it. Normal and weight look exactly the same, but if the package is going down the incline, the frictional force is up. So our equations are going to change a little bit. Our normal force is still equal to mgy, which is mg cosine of 37 degrees. When I look at the forces in the x direction, I have the weight minus the frictional force is equal to mg x. I actually kind of inadvertently changed my sign convention here from the last time, but that's okay. I made down positive and up negative in this case because when I made the weight a positive force, that was making that sign convention. So I'm going to have a new acceleration here, mg sine of 37 minus mu g cosine 37 equals a. And this turns out to give me an acceleration down the incline of 6.14 meters per second squared. So I know the acceleration is 6.14 meters per second squared down the incline. I'm going to use the same kinematic equation as I did last time. Give an initial velocity of 0, and this time a positive acceleration over 8 meters. This is my v final squared. So v final ends up to be 9.9 meters per second. And that is that.